Hello everyone, welcome back to another Geostats lecture video. And in this lecture video, I want to cover the last piece of Morans I. And if you remember back to our previous video dealing with Morans I in R, we said that one of the downsides to Morans I was that Morans I test statistic, right? We have an example of it down here in the console from our previous video, right? That we have a kind of a hard time judging whether or not that value is high or low on an absolute scale. And that's because the Morans I statistic is dependent on the spatial weights matrix input. Now, that being said, there is something we can do to actually calculate the range of possible Morans I values. And the closer the Morans I statistic is to the maximum possible value, the more of an indication we have that Morans I is significant, right? Aside from the p-value testing, right? So what we can do, and I don't expect you to understand this code, especially if you aren't well versed in matrix algebra, but basically we can get the eigenvalues of the weights matrix, and we can return the maximum and minimum eigenvalues. The minimum eigenvalue being the smallest possible Morans I, and the maximum eigenvalue being the maximum Morans I. So if Morans I is closer to the maximum, it's more likely to be significant. If Morans I is closer to the minimum, it is less likely to be significant. So let's go ahead and just quickly run through how we would use this code. Again, I'm not expecting you to understand what it's doing, but the important part is that this return, right, this return range eigenvalues is going to give us our possible range for a given application. Because again, Morans I, part of the problem with interpreting it is that its range is dependent on the inputs. So let's just really quickly go ahead and run this code. So if you don't have this code, and you're following along, just pause for a second. It's 6 lines. You can quickly type it up. Again, we're not using anything other than spdep, the spdep package here to create the function. It's going to take in a spatial weights matrix. That's what this LW is. And then what I've done is I've pulled the lines of code from our previous videos just to quickly demo how this function works. So what we're going to do is we're going to go ahead and we're going to run this code chunk. Bring our console back up. Okay. So all you do to run this, and we're going to run it on the rook and the queen. So we'll call rook equals Moran underscore range. LW is going to equal rook underscore spatial weights matrix. So if we run this, we don't get any errors, which is beautiful. And then if we run rook, if we call rook, so if we scroll, if we make our console a little bit bigger here. So this is our Moran statistic for the rook's case. You'll see that we have a 0.094 as our Moran statistic, and you'll see the maximum possible Moran statistic for that particular instance is 1.03. So you can see that we're pretty close to the maximum possible Moran statistic, which is, again, a strong indication that we're going to be statistically significant. And again, we sort of confirmed that with our p-value, which is less than 0.05. So just really quickly, let me drag this back, split this off again. Let's quickly do one more demonstration for the queen's case. Queen, again, Moran range. LW equals, in this case, we're going to call it on the queen spatial weights matrix. Okay, if we run that, and then we do queen. All right, and you'll see here again, if you remember back to all of our other videos dealing with the Georgia dataset, you'll remember that we didn't have too much of a difference in terms of connectivity. So it makes sense that these are going to be pretty close, but we did have a couple extra lines, right? The queen's connectivity, just a quick review, right? The idea that they can share just a point instead of an edge. So we do have a couple extra pieces of connectivity, and that does reflect in the range, right? By about 0.01 on either side. But again, if we slide this back up, just to quickly compare here. So this is our Queen's case, right? Queen's spatial weights matrix. So this was our test statistic. And you'll see here that with the value 0.092, right? Our highest potential was 1. So we're actually not that close. I'm sorry, I actually misspoke in the previous example too. We actually aren't that close, right? We're roughly in the middle. So that's why our p-value is significant, but it's not super significant, right? 0.02 is not that that low relative to say 0.0005 or 0.005, right? So we're significant, but our test statistic isn't on an absolute scale isn't amazing. So given this information and this information, what I would say is that we are statistically significant, but the overall impact of autocorrelation is probably not as impactful as it potentially could be, right? Because again, the highest possible Morans I is 1.03. Our actual Morans I is 0.09. So hopefully that makes sense. Hopefully the idea that we can get the range of Morans I, that we can take that back to compare to our test statistic and how that relates to our p-value. So hopefully that makes sense. And as always, please reach out. Thank you.